So data-driven decisions is now common practice in many companies around the world. But one looming question that's kind of challenging is how do you make the best decision when you want to optimize not for one objective, but more? The reason this is an interesting question is because many objectives are in conflict, and that results in trade-off decision making. For example, even when we do shopping, right, we constantly compare price versus quality. It's hard to both minimize the price while maximizing quality. And this is relevant for many industries. For example, supply chain management, manufacturing, land use planning, and also, of course, in the very timely drug discovery. In which, in this example, if we want to consider a candidate antibody to be a therapeutic that will cure us, it has to pass many tests, and it takes only one test for it to fail. And nowadays we hear about therapeutics for COVID-ID being available, researched and brought to production within a year, but normally it takes 10 or 12 years. And so imagine a project discovering that something fails after such a long while. And one way to solve for this is the topic of this discussion. It's called multi-objective optimization. And these are the four main ideas that I will be circulating around and I want you to take home with you. Well, first I'm going to talk about the shortcomings of what's called single objective optimization. And that's basically the common practice of what most analysts do when they're dealing with two or more parameters that they're interested in optimizing over. You're all familiar with it, in which we combine it in some way or form, and then we optimize over that single heuristic. And so I'll point out why that's a very limited approach and it yields suboptimal results, and how we can fix this with a technique called Pareto fronts. And then I'll introduce how we can actually use Pareto fronts in the context of genetic algorithms. I'm not assuming that anybody knows what a genetic algorithm is. I'll explain it from scratch. And then I'll talk about applicability in the real world, as we learned from the previous talk, how important that issue is. And the main thing that I hope that you take home with you is understanding the technique enough in its principles to be able to assess for yourself if this technique is relevant for the project that you're working on. So this is just a brief description of what I've been up to in the past 16 years or so. I'm currently a data scientist in a healthcare company. I started off as an academic doing research in observational cosmology. And most relevant for this talk, I spent 2 years in a biotech company called LabGenius, in which we were applying machine learning for therapeutic discovery. And on this note, I want to mention that Pi data has been part of my trajectory as of about 2014 when I came to London. So this is the place to thank all the organizers here in Eindhoven, and especially the ones in London that helped me create a place where I can share ideas and learn more about what it's like to transition from academia to the private sector. So this is a list of topics that I want to go through. It seems kind of daunting, but don't worry. I'll break it down, and hopefully you'll have appreciation for most of what I'm going to talk about today. So with that, I'll define how I'm going to use the term optimization in this talk. I define it as a procedure of finding and comparing feasible solutions until no better can be found. You know, a topic is interesting if Randall Munroe, the creator of XKCD, has a comic strip about it. So I like this one in particular, in which he subjectively distributes fruit according to his preference, both in taste, where you can see he finds the most tasty one to be is peaches, and according to how easy it is to eat, then he ranks seedless grapes as the most optimal. So my question for the audience, and I'll give you just a few seconds to think about it. Which is the optimal fruit that you, as his, let's say, his office mate, would bring him from the kitchen if you want to optimize for both taste and how easy it is to eat? So just think about it. No need to put in your answers. All right, so you might have said peaches, you might have said seedless grapes, some of you might have said strawberries. So the answer is that it was actually a trick question. There's no one optimal fruit, but actually throughout this talk, what you'll appreciate is that these three are considered equally optimal, and we'll
Hello, El. Are you there? I think we lost you for a second. So we're gonna bring you back online. Very good.
Hi, can you hear me?
Yes, yes. So we lost you at the optimal front. So at the optimal fruit decision front.
Oh, and you didn't hear the answer that I gave to that?
You said you just presented the slide that there's a front, right? So maybe take it from there again, if you don't mind. So you asked the question and the slide appeared and then we lost your voice.
Okay, yeah, I think my internet dropped for some reason. So I showed you that there's an optimal front. That's what I showed.
Right.
Okay.
I think you need to share your screen. Yes, there it is. Okay, very good.
Okay, so just to recap, I showed, I showed that there's this optimal front, and the purpose of this talk is for you to appreciate why these are considered equally optimal and what we can actually do with that sort of definition. So just before we get into that, I'll take a step back and we'll explore what you were doing mentally in your mind. And as analysts, what we do in our everyday when we want to optimize for multiple objectives. And these objectives here, I give them boring labels as 1 and 2, but think of it as price versus quality. Or if you're doing hyperparameter tuning in machine learning, then imagine these as being hyperparameters that you want to optimize over. So what you want to imagine is that you're in a dark room with a flashlight, and you're using this flashlight in order to explore directions that you're most interested in. And so what a lot of us do is what we call single objective optimization. So what does that mean? Is that we come up with some ad hoc combination of both objectives, and then we will bore a tunnel in our search space. So for example, here we'll dig. We see there's no solutions over here, and so this is the most optimal solution, and we'll tag that and we'll say that's optimal, and then we'll make decisions based on that. Of course, I did multiplication, but you can do other things, like you can do the mean, and these are cases for max. Imagine you can do max min, and then you'll divide, etc. But at the end of the day, all of these are the same. You're taking all your parameters and you're combining them into one single heuristic. And so this approach is very limited. Here I'll show you another approach of this is, and this is what's done in some laboratories, in which they optimize for one parameter, and then they optimize for the other parameter. And so in this method, they'll say, hey, this data point is we'll consider it optimal. But they could just as likely start it with objective 2 and then go to objective 1 and say this one. And so you're already noticing that something very weird is going here. I made 3 subjective decisions of how I want to explore the space, and I got 3 totally different optimal solutions. And so in multi-objective optimization, what we say is that we want to actually turn on the lights, we want to see the full solution space, and then we want to make our subjective decision of what we consider optimal. For example, here we want to maximize both of these. So we want to get over here, but there's no feasible solution. Remember, we're talking about only feasible solutions. And so maybe our domain expert, which might be yourself or somebody who actually knows more about these parameters, will select, let's say, this one. Or maybe they want to consider more overweighting objective 2 than objective 1, and they'll select maybe this one over here or another one. So how do we quantify this in a more rigorous way? Well, what we say is that we have this we'll have this front called the Pareto front of solutions, in which they are all considered equally optimal. And once we realize that, then we'll make our subjective decision. So more about that later. So what I've defined so far is the limitations of single objective optimization. It gives a limited view of our search space. And with Pareto front, we'll be able to explore the full solution space to make better decisions. But just before I define what a Pareto front is, you notice I used the word subjectivity a few times so far. And that's on purpose. I was dripping it into your mind that as an analyst, I try my best to be as objective as possible in every step along the way of my process. But I have to be, at the end of the day, humble and realize and identify where I make subjective decisions. So in the case of single objective optimization, or that linear approach that I described before, we're making subjective decisions before we're even starting the search. But the purpose of multi-objective optimization is holding on to that, not making that decision, and applying subjectivity only after we finish the search. So with that in mind, now I'm ready to define what a Pareto front is. So if we're looking at solutions, then we can divide them into two. We have what's called the dominated, here highlighted in gray, and then we have the non-dominated, highlighted here in red, and the set of all the non-dominated are called the Pareto front. And their nice property is that because we haven't applied subjectivity, we consider them all equally optimal. So just to guide you, how do you quickly identify the dominated from the non-dominated? For example, focus on K over here. So K is dominated by D, for example. And the reason for that is that a solution is dominated if we can find another solution that dominates it that has a better value in all of the objectives. This is, of course, 2D, and you can extrapolate this to higher dimensions. But here you can see D dominates K, both in objective 1 and in objective 2. Same thing for E, as opposed to what? As opposed to C. For example, C is dominated by D in objective 1, but not in objective 2. Here, of course, I'm assuming that we want to maximize for both 1 and 2. The same but opposite between C and B. We can see that B dominates C in objective 2, but not in objective 1. And so this applies for C, and as well as all of these that are lettered from A to H. Another interesting aspect of this is that we do not care about the relationship of units or scales between objective 1 and objective 2. Again, remember, this could be price versus quality. So you don't have to put monetary value on quality, or hyperparameters, which have totally different scales, totally different units. So this naturally is agnostic to this. And so I know that you're looking at this and you want to say, oh, but D is the most optimal. At the end of the day, yes, we're going to apply subjectivity, but that's only after we get the full snapshot of the solution space. So once we have this, then we can make a subjective decision which way we want to go. Do we want to go to D? We want to go to H, or any combination, depending on how many solutions we can make in our decision, depending on the context. So what I've described so far is I introduced to you Pareto front as a set of trade-off non-dominant solutions. And the reason that we could define this is that we did not make our subjective decision before going to search, but rather we were holding this until after the search. And what this means is that at the advantage of this approach of multi-objective optimization versus the single objective optimization is where now we get like a bird's eye view of the full solution space, and we can make better decisions, as opposed to before. What I showed you is that we were effectively like putting on horse blinders, and that was guiding us to one solution or another that we called optimal, but we saw that we might have preferred something else if we had a bird's eye view.
So just a quick question, Neil. So
yeah.
Thanks for that. The question that came through is, can you maybe share a few practical examples of where in your experience you've kind of used this? And I think you'll be talking a bit about later, but just to kind of ground us to where this is used and where you've used it personally, can you share a few words on that?
Yeah. That will be the lion's share of my talk. Let me just think. Yeah, so I'm going to get into genetic algorithms. Yeah, so I applied it within the context of therapeutic discovery, in which I showed before you have a antibody in which you have many candidate proteins called antibodies, and they have to pass many tests. And I was testing it for 2 parameters of interest. You can imagine something like response of the immune system and potency, for example. And it's a way to I had a machine learning model that, given a sequence of antibodies, I could predict those parameters, and that way I could suggest. So once we have the machine learning model, I could propose to a protein engineer who orders those sequences, which sequences to order. If that didn't make any sense, well, I'm going to get back to that later, but that's just to whet your appetite for where I personally have applied it. And I'll show this also later on in this case study in terms of you can use it for hyperparameter tuning.
Okay, very cool. Thank you.
Yeah. So now I wanted to, now that you have a basic understanding of what Pareto fronts are, I want you to have a feeling for, is this relevant for the projects you're working on? And just before I do that, we have to understand the parameters that we have and a useful splitting between decision space to objective space. So objective space is what I've been describing so far. That's what we're actually interested in. That's what we want from our system. So that you can imagine that that's being the quality, or that's being the price of the project, where decision space is what we actually have control over. So just to give you two examples of this is, for example, there's the classical problem called the knapsack problem, in which what you have is you have packages, and each one has a monetary value and it has a weight, and you pack these packages in the knapsack. And what you want to do is you want to optimize both. You want to optimize where you want to maximize the value of the package that you select, but you also want to minimize their weight. And so those are two objectives. They're obviously in conflict, right? The more packages you put in, the more weight it's going to gain. And so what do we have control over? What's our decision space? Well, our decision space is which subsets of packages do we choose? And then our objective space is the calculated weight, or the calculated value. And these arrows are important because that shows that we have we have a function that goes from the decision space to the objective space. Another example is hyperparameter tuning, right? We're not actually interested in the hyperparameters, but that's what we have control over. What we're interested in at the end of the day is metrics. For example, precision, recall, accuracy, depending on the application that you're working on. And another important factor is the mapping between them, right? If we change the hyperparameters in order to get to the metrics, well, we have these pipelines. We have the training and the testing of our data. And so this might be a function of time, which might be crucial. So what I'm trying to say is multi-objective optimization relevant for your project? Well, of course, it depends. And it depends on, first of all, that you have full control over your decision space. If you have control over your decision space, for example, the hyperparameters in the model you want to tune. The second thing is you need an inexpensive mapping from your decision space to your objective space. For example, a counterexample of that is, let's say you're a marketing firm and you have to make decisions between approach A, B, C, or D, and the metrics of interest, let's say click rate or anything like that. Let's say that's a function that will take time in order for you to get, like, you have to put into the field. It will take a few days until you get the feedback. So that's would be like expensive feedback. So then it might not be relevant for you. But that said, if you have a decision space and you have some sort of model, if it's deterministic or probabilistic, to get to the objectives you're interested in, then you're golden. Then you're good to go. If this is something that if you can brute force your way to the full solution space, then you can literally open up an Excel spreadsheet. You can draw a Pareto front, sit with the domain expert who actually makes the decisions, and choose which solutions you want to go forward with. Most likely, though, you're going to deal with an intractable search space. So that means you won't be able to brute force your way to all of the solutions, but you'll be able to get some sort of proxy of what the solution space from your bird's eye view actually looks like. And in that case, you will want to use a stochastic algorithm that's intelligent in the way that it navigates through the solution space. So one that practitioners like to use is called genetic algorithms. I'm sure that you heard the name. I'm not assuming that you know how this works, so I'll describe it. For those who do, I will point out where Pareto optimization actually goes into this calculation. Because a lot of people use genetic algorithms, but they do it with single objective optimization, not realizing the power of Pareto fronts. And that's one of the objectives of this talk. So genetic algorithms are great to use for when you're dealing with intractable combinatorial space. One reason is that you can get multiple solutions, right? In Pareto front, we want multiple solutions. We don't want to end up just with one. And also, you can apply techniques like niching. That means that you don't get into, let's say, into like a local minimum or something like that. And so you can apply like send your population to many regions. So we have this algorithm for about 60 years now, and it's based on evolution, in which our solutions are considered a population in which we have the individuals within the populations compete between them, and we have them passing on their traits to the next generations through their children. This is a nice way to summarize it: explore as much as you can and keep the best. There are various, this is one type of architecture. And so I'll just guide you through this so you have a basic intuition for a genetic, how a genetic algorithm actually works. So you start off with an initial population. So no need of knowledge in biology here, but this is a representation of proteins. So this is relevant to the work that case study that I'll show later on, in which this is a sequence in which in white we have, so each letter, represents a chemical compound called an amino acid. And so there are about 20 in nature. And so in white are the ones that we're holding fixed, what biologists call wild, or we can consider them as the vanilla. And in red are the mutations that we're inducing. It's fine not to think in terms of biology. There's actually the knapsack problem is a perfect analogy in which the whole, like whatever this is over here, 15 or 20 or 10 actually is amino acids is the full knapsack, and each position here is a different package, and so each letter represents a different package you can change. Or imagine this as you have 10 hyperparameters, and each letter represents a value. Each position is a different hyperparameter, and each letter is a different value. Okay, so all of these are perfect analogies for what I'm going to describe. Keep a mental picture of whatever you prefer. Okay, so we start with the initial population, and this is our decision space. This is what we have control over. For example, I worked with protein engineers, and they can manipulate these amino acids, which is pretty far out. But that's not what we're interested in. At the end of the day, as the analyst, we're interested in the objective space, right? For example, potency and reaction to the immune system, for example. And so for each solution, we have both of these values, and we can put them in a plot like this. And by now your eye is kind of let's say I want to maximize objective 1 and objective 2. By now your eye is already kind of looking hopefully towards the optimal set of equally optimal solutions, otherwise known as a Pareto front. And of course, that's this envelope over here. So these are the ones in a very naive selection function are going to be selected for the next generation. And then we do transformations in order to get similar results for similar solutions, converting them from parents to children. So we have something called crossover, which is similar to what happens with our chromosomes, in which we have one from each parent, and then we have mixing of the information between them. So here we just have a crossover. So child 1 has this half from parent 1, and this half from parent 2, and vice versa for the second child. Another transformation we can do is we can convert one amino acid to another one, or in the case of the knapsack problem, just change one package for another package. And so we'll do this in many iterations, and we can, let's say, stop after 40 or 100 iterations. And at the end of this process, what we'll have a list of all the individual sequences that we examined, and we'll have all of the scores. So what we get at the end is a list of our decision space that we have full control over, and our objective space, what we actually want. So now what I'll show you is an animation of going through many iterations of this, just so you see how this evolves with time. And here I'm actually going to start with a non-realistic example in which both objective 1 and objective 2, this is being minimized, and so we want to get to the X, in which they actually agree. So here you see this is a Pareto front of actually 1. And this is an animation, which I'll start, and you'll see them going all the way over here. More realistically is if they are in conflict. And so here we want to maximize for both. And so we want to get to the X. This is like a classical looking Pareto front, and which starts over here. Again, blue is the Pareto front. The gray are the dominated. And now what you'll see is this Pareto front like approaching X, but never really reaching there. So let's say I start from over here. And you can see the envelope moved forward with large jumps at the beginning, but then little bit by bit, it's improving. We saw improvement. Okay, so what I showed you right now is that in most real life scenarios, you're going to have to deal with intractable spaces, and so you'll want a smart stochastic search mechanism to navigate through it. And I showed a genetic algorithm as one option in order to explore the space. And the reason is it works naturally with Pareto fronts, which come into its selection function. And now I'll talk about real world applications. So let's say that you have, you realize that you have everything that's required. You have your decision, you have full control over your decision space. You have an inexpensive mapping to your objective space. And let's say you have an intractable search space, so you decide to go with genetic algorithms. Then I suggest for prototyping purposes in Python, this module called D. Yes, this is with A because it's evolutionary algorithms in its acronym. And it's very simple to use, and you can parallelize during search. And it has a very simple API, a fairly simple API to use, in which what you can see here is a snippet of my code in which I'm feeding custom-made functions, for example, mate, mutate, into the toolbox registry. And so the nice thing is that I don't have to script for myself Pareto fronts. I described something very simplistic before, actually, and what they have is the frontline algorithms. And so this one, for example, by name is called, its acronym is SPEA2. And so they have this all built in. And so if you want to take this on, I highly recommend this module. And now I'll talk about a case study, something that I actually worked on in my previous job. And so I worked in Lab Genius, which is a biotech company which have their own wet lab. And what they're doing, they're generating their own data in order to use machine learning to discover therapeutics. Their focus is on Crohn's disease. In this case study, I'm actually using publicly available data, so not their data, but just to showcase like the capabilities of what we're building there. So the data at large is antibodies that are scored for binding, and I also model them for something that I'll call potency. Those details don't matter. What is interesting is that of a length 200, there were 20 places that were mutated. So here I just combine all those positions together just for simplicity. And what you can see here, oh, by the way, so each position can have 20 combinations. 20 to the power 20 is 10 to the power 26. So that's intractable. That's why I use genetic algorithms. So what you can see here is that it's highly skewed towards the wild type. Again, so what you can see here dominating is the wild type sequence. And then you can see 10% of these, what's squished over here, are the different amino acids that they tried mutating within their data set. So what we had is a machine learning out. Yes.
Can I ask a question from the audience?
Sure.
So Jeroen is thinking, going a little bit back to your previous slide about the knapsack problem. He's saying, I'm thinking about formulating the knapsack problem in the context of GAs. The knapsack places a constraint on the genes. Not all crossover or mutations will result in feasible solutions. How would you account this for a genetic algorithm?
Sorry, could you repeat the question?
So there's some kind of a constraint on the knapsack problem. So not all crossovers or mutation will result in feasible solutions. I suppose it depends on how you design your genes, right? But how would this work for something like the knapsack problem?
Yeah. So, the question is for the knapsack, whether, I mean, so yeah, first I can answer for biology, like there are like infeasible solutions, there are combinations that aren't feasible. So that's something that you can remember that in Deep, I showed that I could do like custom functions. And so I can take all those real life scenarios into account. And so what that means is I can, so if I'm maximizing, for example, then I can give a very low value, for example, for that. Or I can do like, or I can introduce like cutoffs in my algorithm. And in the knapsack, ask me again at the end if it wasn't clear, and I'll address that as well.
I think it's clear. So in your algorithm, it's, yeah, he's saying that sufficiently answers my question.
Oh, cheers.
So basically you can just kick out the bad genes or have a very low score for them, so they won't be crossover, right?
Yeah. So anything that's unfeasible, then you can dictate that. Yeah.
Okay, thanks.
So what we had basically is a machine learning model in which, given a sequence, we can predict for binding and potency. But what I want to do is I don't want to give the protein biologist a machine learning model. I want to give them actual sequences. And so what my task is to do is to use the machine learning model as my compass to navigate the solution space in order to climb the hill as much as possible to give the sequences that are most likely to succeed in our objectives. And, so that's the task at hand. And so what I'm showing you here is an animation of the genetic algorithm of what's happening in our decision space. Again, what we have control over. So I'll just rewind the video. It's not working there. So here I'm starting at iteration 0. So whereas before I showed the frequency of the amino acids, here I'm showing the change in frequency. So the way to read that is that if T was 90% at the beginning, now it's at about -50. So it's actually like 40%. But I'm just highlighting here on the bottom, that's much less than what it is in the data. And then you can see like the competition between the wild type T to all the other amino acids. And so with time, you can see that, for example, over here, the wild type W is rejected and it prefers actually A in this position, but in other position, actually it's fine with the wild type. There's no other preference for any other amino acid. So that's something, so that way, it's a way for me to visualize like what's happening in the decision space. But of course, we're interested in the objective space, right? These are like the potency and binding and immune response, etc. So it started off over here, and you saw like a jump over here, and like slowly it's pushing this envelope more and more so towards this direction over here. By the way, all these visuals are made with Matplotlib.
Yeah, if I can ask a question, so to get this
Yeah.
Pareto front, so you mentioned the algorithm that's inside a package, right? But I suppose it does some kind of smoothing around the Pareto front, right? Because otherwise, it's, I mean, yeah, do you know what it means? How does this work more or less?
No, there's no requirement of smoothing of the function. So he's referring to the fact that it looks kind of rigid. And that's totally fine, because what we're doing is we're selecting individuals rather than creating a continuous function. Does that answer the question? So this is all discrete. There's nothing continuous over here.
So just to make sure I understand, and maybe I missed this, yeah, so excuse my ignorance here. When you talk about the Pareto front, it's not that you're looking for a mathematical equation independently of which dimension you're looking at to describe that Pareto front. What you're really looking towards is discretely visualize what that would look like, right? And you have kind of like a cutoff front, but you're not looking to create a spline or something like that to describe that
No
front.
splines. Like literally, like you see this over here, I'm literally like selecting that. The fact that it has an X on it, that means it's being selected for the next generation. I'm selecting this solution.
Right. And the fact that our minds see that makes a line is just that's what our minds see. It doesn't mean that that's what you're effectively doing, right? So in this example, it feels very natural to draw a line there, a vertical line.
Yeah, that's an excellent point. No, but in this animation, wherever you see an X, that means I'm selecting that particular solution for the next generation.
Yeah, so you just take the top, you take some kind of, the top ones, and then you do them all across the line. Yeah, I see. But you just, I mean, what I meant with smoothing, you do need to, okay, never mind. I'll maybe, let's continue and maybe rephrase my question afterwards.
Yeah, no, I admit that
Amiibo discussion.
the topic can be quite abstract. Yeah, the topic can be quite abstract, but yeah. Okay, so we're nearly there. I just want to mention another case study. So yeah, so I was wondering like how many people are actually using this for hyperparameter tuning as a use case, because there again we have multiple objectives that we're looking to optimize from. And so sure enough, I found this study by data scientists in SAS, in which they worked with various clients of theirs. And so here I'm just highlighting one of their projects with an organization called Donors Choose, in which they provide a platform for teachers to request for materials for projects that they're working on. And their challenge is that they were overwhelmed with how many requests they have for review, in which over 600,000, about 20%, they considered are worthy for review. And so they wanted to automate that. And one of the main objectives that they wanted to reduce their false positive rates. So they want both misclassification, but mostly like reduce the false positive rates. And so, yeah, so here you have the link to the actual study. I won't get too much into detail. I'll just point out like this nice result that they show, and which what you can see here is, so what they started off is they had their vanilla machine learning algorithm here, this black dot called default. And so this is what they have, about 15% misclassification and just south of 4% in FPR. And so they want to minimize both. And so first they start with the single objective optimization. That's your familiar F1, AUC. And so you remember I talked about boring to a certain direction, and that's exactly what it's doing. You can see these single objective heuristics like going like over here, like reducing this classification, but actually doing worse in terms of FPR. So what they decide to do is, well, they'll apply the Pareto front approach. And that's what you see here with all these dots in which the green highlights the Pareto front itself. And then, so note that with F1, they made a subjective decision before the search, but now they're going to make a subjective decision after the search. So they said, well, we don't like this cutoff, this funky region here at this very, the steep thing over here at 15%. So they ran it again. This is a zoomed in version in which they ran it again, in which they constrained their search space to under 15%. So to answer the question from before about what you consider feasible, they said, well, we don't consider anything above 15%, which was our vanilla, as feasible. We want anything below. And so what you can see here is these triangles are performing slightly better than the green. But the most important thing is they feel they made a better decision. Instead of compromising on the standard single objective optimization approach and being over here, right? Their starting point was way over here. They actually went down here. And so their final result was that they improved the FPR, by about a relative 8%. And they reduced the misclassification by an absolute 5%, from 15% down to 10%. And so I think that's it's encouraging to see that data scientists are starting to apply this in the context of multi-optimization, but there are very few of them. And so that's why I like to promote this so people, including myself, will start doing. So that's it. I just want to mention that if anybody's interested in learning more about this, I actually have a hands-on tutorial that I posted on GitHub, in which it comes with 30 minutes of basically similar content that what I presented here, as well as 1 hour in which I go through the tutorials. I have Jupyter notebooks in which you can clone or you can use in Colab. I'll very briefly show, here it is in GitHub. So you have all the links to the videos, and then you have links to tutorials. So here's one. It's the notebooks are fully annotated, and I challenge you with questions, so just to see how much you're understanding. So yeah, so if you're interested in this topic, then please consider that as a resource. Here I'm providing more resources for anybody who's interested in learning more about the topic. And the most important takeaway, is this relevant for what you're working on? Can you actually apply this? So you should apply this if you have more than one objective that are in conflict. You have full control over your decision space, and you have an inexpensive mapping from your decision space to objective space. Most likely, you're going to deal with intractable search space. In that case, I suggest using genetic algorithms. And if you want to use Python, then I suggest using Deep as a prototyping tool. So with that, I'll just mention also one more lesson from preparing for this talk. My personal computer actually crashed yesterday. That's what you're seeing over here. So my takeaway is very good to have a backup, let's say in Google Drive, of your talk when you're preparing for a talk. So yeah, so with that, I'm glad to take any questions either here or on the island.
Okay, well, that's a very great lesson, takeaway lesson. Always have a backup. So maybe I can rephrase my question a bit. So how, okay, so we can look at this figure as an example, right? Mm-hmm. So basically, how you make the frontier. Okay, so there's some kind of a function, right? Maybe one axis plus the other axis, whatever score is there. And then you take for your genetic algorithm, you take the top fixed amount of them for your next generation, and that's how you build the boundary. Or
so I look at the full solution space. So you're asking me, how do I select the population for the next generation? Is that the question?
yes, and what's your function basically to compare both skills, maybe more or less, because it needs to come together at some point to do your selection, right?
You mean between the decision space and the objective space?
Yes. So if you select your next generation, there might be one completely doing very well on one axis and very well on the other. So how do you balance between those, right? I mean, there's some kind of skill in there that you need to impose.
That's a fair question. Okay. So this is going more into detail about that's a fair question. Something I have discussed. So, and it's something that I go into fair detail within the tutorials. So when you go from one generation to another, you have to define parameters. For example, how many solutions do you want to go to the next generation? So let's say you start off with a population of 20, and then based on that 20, you create, let's say, another 40 or 60 more children. So let's say you have a population that's competing for the next generation of, let's say, 100 solutions, and you have to select 20. Okay, so then you have three options. Either you have a Pareto front, right? You identify the Pareto front, and let's say you count exactly 20. Okay, then a simplistic algorithm will say, okay, let's just choose all the 20. I don't care how ridiculous it is. Let's say the ones over here. I don't care that it's very low. We're not making any subjective decisions. We're holding that urge because I can hear it in your question, like, oh, this is doing really bad, right? But I don't know the scales yet. I haven't determined that. I'm agnostic. So I don't know how bad being over here is because I haven't made that decision yet. So that's the case in which I predefined. I want to select out of 100. I want to select 20 for the next generation. My Pareto front happens to be exactly 20. Then I'm golden. Well, what if, let's say, my Pareto front is 20, but I told it. Well, let's say I decide I want to take 20, but I actually have only 19 on my Pareto front. So that means, well, I'm taking my whole Pareto front of 19, but then I have to choose another one from the next layer. So I take out the Pareto front, and then I select the next layer of Pareto front for my solution space. So so let's say I selected all of these. Okay. Let's say these are this is what 1, 2. This is, let's say, 8. Let's say my Pareto, I decided I want 10. Well, these are all selected, but then I have the next Pareto front, which comprises this one, this one, this one, and this one. So out of these, I have to choose 2. Okay. And so there's a simplistic way to go. There's a simplistic way to go about it, but then there's the state of the art. So that's what I mentioned in Deep. They have like state-of-the-art algorithms, and I give references so you can learn about how to go about choosing that. So the state-of-the-art, what they do is they look at the density of solutions. So they account for the density. So if there are 2 solutions in a dense region, they'll select one of them as opposed to 2 of them. And also they some of the algorithms to maintain like the edge cases because they are interested in diversifying. That's one key aspect I didn't talk about in this, and I do in the tutorials, is the importance of diversity.
Yes, exactly. Yeah, that touches upon my question because you can see them well spread around the front, right? But that doesn't really happen automatically, I would believe.
Yeah. So maybe I should have. Yeah, I could have made my answer much shorter, but just emphasizing diversity is a key aspect for genetic algorithms.
It was a bit of an open question, so I need to explain a lot of things. So I have another question from Jessica.
Sure.
Have you seen Pareto optimization in combination with other algorithms instead of genetic algorithms? Any good pro-con takeaways?
Have I seen? That's a good question. So I mean, it can work with any, not any stochastic. Nothing comes to my mind at the most. Most of my exploration of the topic, when I went to the literature, most of the experts talk about genetic algorithms, but there might be others, but I'm not aware of it.
Yeah. Okay, and just get, I think pretty much the same question as I had, because she now says, I think you just answered my second question also. So that's great. Yeah, but it's an interesting question whether it works with other algorithms. But I think, so what's happening with the Pareto front is some kind of an or statement going on, right? Because you're looking for both either complete one option and the other. So I think with other methods, it would be a little bit tricky because you would more or less still need to translate it into some kind of an objective function or something like that. So
it really depends on the case. I mean,
yeah.
At the end of the day, like there's, I like to separate in my mind the decision space versus the objective space. What I described here is with decision space that is quite discrete, and an objective space that's discrete. But but it is possible to look at like break down a continuous function, continuous solutions and just discretize them. So I think that's done as well. But most of my experience has been in the discrete space.
Yeah. Okay, and maybe one last question. The examples you show is with a few dimensions of two objectives basically. But you're generalizing it towards multi-objectives. But so what's your experience in, I can imagine it's inconvenient to have too many objectives, right? Because then you get a super complex Pareto front that it's really hard to interpret. What's your experience in having many objectives?
Yeah, well, I mean, on the one hand, there's two challenges. First is the curse of dimensionality, in which things become too sparse. So you want to keep it. I admit that I haven't looked beyond like 8 objectives or something like that. I think I kept it to about 8. And the way to visualize it to myself, I looked at like just 2D plots of the combinations. Just to get a feel for what's going on, if there are more regions of interest or not. But yeah, that's a challenge.
So you just make a bunch of 2D plots,
plotting
each of them against each other or something like that, and then you can see a little bit where your main trade-offs are in objective functions.
But also, those visuals are useful. Those visuals are useful because then you can identify parameters that kind of agree with each other. And then you can choose one over the other and reduce your space to make it more simple, for example. Or because they kind of agree, you can actually turn those two into a single heuristic or something like that. But the important thing is the ones that that clearly conflict and have no correlation between them. Then you want to be agnostic of any relationship between them. And then so I think looking at correlations actually would be a good idea. If you do that up front before that might save you time in your search if you examine the correlations.
Also, if you need to ask your users or stakeholders, like, okay, you need to make some decisions on, you can pick all the objectives, right? Then you can search through them, and the animation that you showed, there's like quite some density in the top right corner. Well, then you have quite good alternatives for both objectives, right? So you kind of want to filter down between when it looks more like this one that you see here, because that's where decisions need to be made, which one is more important, I guess.
Yeah, my experience with most stakeholders, all they want is like a list that they can just go through. And it's nice to know if they want to take agency on why the decision was made, and that's great, then it's the job of the analyst to come up with meaningful visuals for them. That's always a challenge, and it's a fun challenge I always find. But a lot of times my experience with stakeholders is just give me a list. I trust your decisions. And but sometimes I admit that, I have to consult them because they're the main expert of which way to go, but sometimes they don't know themselves and they leave it to me to make the decision.
Yeah.